Welcome, everyone. I am absolutely thrilled you're joining us today because honestly, we are looking at an environment that is simultaneously the most alien and yet the most vital to our very existence. We're talking about the deep ocean. It's this massive realm of terrifying mysteries, literally impossible physics, and, as we're recently discovering, some incredibly urgent climate realities. We're going to explore what we don't know, which, spoiler alert, is a lot, and the really frightening implications of what we are finally starting to measure. Okay, so let's just dive right into our roadmap for this explainer. We'll start with the terrifying unseen frontier, then look at mysteries of the abyss, surviving the impossible, looming climate tipping points, predicting ocean anomalies, and finally, processing the unknown. All right, Section 1, the terrifying unseen frontier. Why the ocean terrifies scientists. I want to pose this question to you right off the bat, because it really frames everything we're about to discuss. Why is it that human beings have mapped way more of the surface of Mars, a planet literally millions of miles away, than the floor of our own ocean? It sounds totally counterintuitive, right? But it actually all comes down to physics. The reality here is pretty stark. Space exploration is massively difficult, for sure, but it does offer predictable orbital mechanics, clear sight lines for mapping, and radio waves that travel super easily through a vacuum. The ocean? It is the exact opposite. Water actively absorbs light. As you descend, the reds disappear first, then the yellows, until you are left in total, absolute darkness. It also completely swallows radio signals, meaning your GPS and standard telemetry are completely useless down there. We literally have to map it using slow, painstakingly difficult sonar pings. Which leads us to this absolutely terrifying metric. Despite all of our modern technology, the drones, the advanced submersibles, less than 0.01% of the deep sea floor has been directly observed by human eyes or cameras. The vast majority of our own planet is completely unobserved, just kind of inferred by distant acoustic echoes. Moving on to Section 2, Mysteries of the Abyss, Sounds and Sinkholes that Defy Explanation. So take the Tamja Blue Hole, for example. Blue holes are essentially these ancient sinkholes that just filled with water when sea levels rose. Tamja is the deepest one we've ever discovered, plunging down more than 1,372 feet. But it's practically invisible from the surface, almost like nature was actively trying to hide it. And what's truly bizarre is the data researchers got when they dropped a profiler into it back in December 2023. Normally, water gets colder the deeper you go. But past 1,312 feet in Tamja, the water suddenly grows warmer and saltier. It actually matches the chemistry of the open Caribbean Sea, even though it's completely isolated. Scientists are still scratching their heads over how that's even possible. And then there are the mysteries we can literally only hear. This is the upsweep. It's a reoccurring set of completely unidentified sound recordings detected by NOAA hydrophones all across the Pacific Ocean. It was first recorded in 1991, and unlike other famous ocean sounds that were just random single events, the upsweep actually returns in a seasonal pattern. Plus, it's loud enough to be heard across the entire Pacific Basin. Is it some giant undiscovered species? Is it deep-sea volcanic activity that somehow shifts with the seasons? After more than 3 decades, there's still no officially accepted explanation. Of course, we absolutely can't talk about the abyss without bringing up the biology. We estimate that roughly 80% of deep-sea species remain entirely undescribed, but the ones we have found, they are wildly creative. We've got the red-lipped batfish, which navigates the floor looking exactly like a bat that applied way too much lipstick. We have sea pics, which are these adorable translucent sea cucumbers that actually act as deep-sea babysitters, harboring juvenile crabs under their bodies to protect them from predators. And then we have sea angels, which aren't jellyfish at all, but rather these free-swimming, pulsating sea slugs that just hover around like apparitions in the dark. Section 3. Surviving the Impossible. The brutal physics of deep ocean exploration. So, picture this. Down at the edges of tectonic plates, the Earth's crust splits open and creates these hydrothermal vents. These black smokers eject fluids at temperatures topping out over 400 degrees Celsius. That is literally hot enough to melt lead. Under normal surface conditions, that water would instantly vaporize into steam. But down there, the crushing weight of the ocean above is so immense that it physically forces the water to stay liquid. It's wild. Because of all this, the margin for error we face when operating in this environment is razor thin. A single submersible dive can easily cost upwards of $80,000. And the physical risks are just monumental. You're constantly balancing the need for power, which means using high-density lithium-ion batteries that risk thermal runaway under all that pressure, against the structural integrity of your titanium hulls. If even a single weld is imperfect, or a viewport flexes just a millimeter too far, the ocean simply doesn't forgive. Like in 2014, the submersible Nautier imploded at 4,300 meters down. The pressure cycling just gave way, and in less than 1 second, the vessel was completely crushed. Every single mission down there is a high-stakes gamble against physics. Which brings us to Section 4, looming climate tipping points. What we do know is terrifying. Okay, so one of the most absolutely critical threats we're looking at right now is the potential collapse of the AMOC, the Atlantic Meridional Overturning Circulation. This is a vital ocean current that brings warm tropical water all the way up to Europe and the Arctic. It's essentially the climate engine of the Northern Hemisphere. But we are currently triggering a devastating feedback loop. It works like this. First, human emissions cause the Arctic air to warm rapidly. Because the air is warmer, the ocean water cools much slower than it used to. This warmer water is less dense, so it doesn't sink as quickly to form the deep return current. This slowing allows more fresh rainfall and glacial melt to pool on the surface, making the water even less salty and therefore even less dense. So the sinking slows down even further, the loop just keeps amplifying itself, and the entire current threatens to completely shut down. Now, for a really long time, standard models suggested a shutdown before the year 2100 was pretty unlikely. But new modeling that extends further out is showing that the tipping point, that exact moment a shutdown becomes basically inevitable, is likely to be passed in just a few decades. Even under the most optimistic, low-emission scenarios where we actually stick to the Paris Agreement, models are showing a shocking 25% chance of an AMOC collapse. And if that happens, it would plunge Western Europe into extreme cold, totally shift tropical rainfall belts, which would cause massive global food shortages, and drastically raise sea levels all along the U.S. East Coast. And while those ocean currents are slowing down, the water itself is fundamentally changing chemically. We're seeing a really widespread phenomenon called aquatic deoxygenation. Our oceans, our lakes, and rivers are quietly running out of oxygen. It's driven by human-caused warming and nutrient pollution, and this oxygen loss disrupts entire food webs, threatening everything from tiny microscopic life all the way up to sharks. Scientists are now strongly advocating that this dissolved oxygen loss be formally included in the planetary boundaries framework, right alongside things like climate change and biodiversity loss, simply because it fundamentally threatens the stability of our entire Earth system. All right, Section 5, predicting ocean anomalies, finding patterns in the chaos. So, when you can't physically see what's happening in the ocean, you have to model it mathematically. Researchers use these incredibly complex, nonlinear simulation models to predict things like oceanic rogue waves. These are massive, totally spontaneous surface waves that can just devastate shipping and coastal infrastructure. By factoring in initial wave perturbations and running these high-order equations, scientists can essentially map out the mathematical probability of a rogue wave forming straight out of the chaos. It's all about finding the hidden underlying structure buried within millions of data points. Section 6. Processing the unknown. How scientists and creators make sense of fragmented data. So the crucial point here is that our understanding of the deep ocean really isn't like our understanding of a forest or a mountain range. It is entirely an act of assembly. Oceanographers are constantly having to stitch together these fragmented sonar echoes, inferred shapes, chemical readouts, and complex mathematical models just to form a somewhat coherent picture of a world they can almost never directly look at. Interestingly enough, synthesizing massive amounts of complex, disjointed data to find a coherent narrative is exactly what we do behind the scenes here. This explainer was actually created with the help of AI research tools, including Notebook LM for information analysis and structuring. And of course, all content was reviewed, edited, and adapted by the creator to ensure complete originality and accuracy. It really is all about bringing clarity to the chaos, you know? Whether you're an oceanographer modeling deep-sea currents or a researcher building an explainer. I want to leave you with this final, really pressing thought. The deep ocean is not just some dark, empty void. It is a highly active, incredibly complex engine that literally drives the climate of our entire planet. And we are currently in a race against time. So the big question is, can we map these final, terrifying mysteries and understand the actual mechanics of the abyss before these looming tipping points completely rewrite the future of our world? It's a massive race between human ingenuity and the sheer, unyielding forces of nature. Thank you so much for joining me on this deep dive today. Keep asking those big questions, and I will see you in the next explainer.